Electromagnetic interferences is considered one of the serious disturbances generated by the external source that affects wireless signals and systems by electromagnetic induction, electrostatic coupling, or some electromagnetic conduction. In this unit, we will discuss the effect of electromagnetic interferences on wireless communication system. We will discuss detail about the EMI compliances and standards. It play a very vital role for the design of wireless communication transmitter and receivers. And then finally, we discuss about EMI reduction, that how we reduce the electromagnetic interferences as much as possible for a smooth and efficient wireless communication system. An additive white Gaussian noise channel model is widely used mathematical model in wireless communication theory to represent the effects of noise in communication system. It assumes that the noise added to the signal is a wide and equal power across all frequencies and follow a Gaussian probability distribution function. The properties of AWGN channel model are as follows. Firstly, additive. The noise is added to the transmitted signal without altering the characteristic. It is a white. White means that the noise has a constant power spectral density across all frequencies. This assumption simplifies the analysis and allow for straightforward calculation. Similarly, Gaussian, this model assumes that the noise follow a Gaussian probability distribution, meaning it has a symmetrical bell-shaped distribution. This assumption is often justified by the central limit theory, which states that the sum of the sum of many independent random variables tends to follow a Gaussian distribution. This model is the simplest mathematical model for wireless communication channel is the additive noise channel, which is a very textbook model as illustrated in the figure. In this model, the transmitted signal ST is corrupted by additive random noise, which is represented by NT. And physically, the additive noise process may vary from electronic components and amplifiers as the receiver of the communication system, or from interferences encountered in transmission, as in case of radio physical, radio signal transmission. Textbook model is additive Gaussian noise channel model, which is a very simple channel model. And if the noise is introduced primarily by the electronic component and amplifier, which are used at the receiver side as well as the transmitter side, it may be characterized as a thermal noise or many other type of noise. This type of noise is generally characterized statistically as a Gaussian noise process. Hence, the resulting mathematical model for the channel is usually called the additive Gaussian noise channel. Because this channel model applies to the broad class of physical communication channel, and because of its mathematical traceability, so another thing is simplicity. This is a predominant channel model used in our communication system analysis and design in the first step. Channel attenuation is easily incorporated into this model. And when the signal undergoes attenuation in the transmission through the channel, the received signal is simple RT is equal to AST plus NT, where ST is the input signal and NT is the noise. And A represents the attenuation factor, and RT is the signal received at the receiver for wireless communication system. In some physical channels, such as wireline telephone, even in steady state wireless communication channel also, filters are used to ensure that the transmitted signal do not exceed specified bandwidth limitation, and thus do not interfere with one another. And such channels are generally characterized mathematically as a linear filter channel with additive noise, as illustrated in figure channel output, where output at the receiver signal RT is equal to input signal ST, transmitter signal, convolution with ST plus noise. And if we incorporate the convolution equation, then it becomes very simple integration from minus infinity to infinity, h a tau plus s t minus tau, d tau plus nt. So this is the overall response, impulse response, or some combination of the convolution response of the received signal, and which is incorporated very simple mathematically with the help of simple linear filter function, where HG, as I've already discussed, is impulse response of the linear filter and denotes some convolutions. And here we can apply further, incorporate many parameters and many other characteristics of the filter in order to make it more and more complex, to make it compatible with the given channel properties as required for wireless communication system. Physical channels such as ionospheric radio channels or underwater acoustic channel also will result in time-variant multipath propagation of the transmitted signal, may be characterized by mathematically as a time-variant linear filter. Such linear filter are characterized by time variation channel impulse response, where h tau t is the response of the channel at time t. Due to the impulse applied at t minus tau, the tau represents the age, left time variable. The linear time variant filter channel with the altered noise is illustrated with the given equation, where an input signal S3, the channel output signal is RT can be written as RT is equal to S3 convolution ST tau T plus NT. And then we apply the integration equation of the convolution, and a good model for multi-path signal propagation through physical channels such as ionosphere, as we have discussed, and at a frequency below 30 megahertz. And mobile cellular phone is a special case for the equation in which the time variant impulse response has the form of H tau t, which is given here, summation sign AKT as t minus tau k plus nt. And this is the very simple mathematical equation for linear time variant filter channels, and where AKT represents the possible time variant attenuation factor for the L multipath propagation distance. If equations are substituted in these two equations, the received signal can be easily calculated from the given equation. And it is realized that in some special cases, as discussed above, the linear time variant filter provide very efficient and very practical results. Hence, the received signal consists of L multipath component, where each component is attenuated by AK and delayed by tau k. And the three mathematical models, as we have discussed earlier, and describe about the adequate characteristics of a large majority of physical channels encountered in practice. These three or channel model we have discussed for AWGN are used in this text, in this course for the analysis and design of the communication.